Now in DeepMind, and tell us about interactive approach, debates, and AI safety. It's really opening a day where that's going to be the focus on much more theory-centered, maybe, than we had in the previous weeks on NLP. Thank you.
Thanks, Doubly. So the name of this talk is Interactive Proofs, Debate, and AI Safety, and I'm going to sort of talk a lot about the background here because motivating why we're doing this at all is kind of a big part of it. Then I'm going to talk about some work that we've had recently with myself and Georgios Piliouros and Jeffrey Irving at DeepMind, Jeffrey formerly at DeepMind. So let's get started with the way things are. So this is the current sort of AI or LLM or whatever you want to call it paradigm. You spend a huge amount of money, shocking amount of money to train a really, really big model. Yeah. A huge amount of money to train a really, really big model. And then after that, you kind of like, it's kind of weird. You have to like prompt it in weird ways to get it to say anything reasonable. And so you do something else to make it do what you want as opposed to like, just weird other stuff. And the training signal that you use to make it do what you want is this. You just kind of like approve or disapprove. And sort of there's a discrepancy between the smallness of the thumbs up and the largeness and complexity of the model. And so, you can ask yourself, is this a reasonable thing to do? And should we expect this to work at all? Well, empirically, it kind of works. Like RLHF works, the models get a little bit better. And but what I'm going to say in this talk, and is sort of the main theme here, is that we need methods to amplify this training signal to provide accurate supervision that scales to superhuman AIs. And this is going to be made very formal, although this is a very vague statement, through sort of normal things that have been studied in complexity theory since the invention of complexity theory. So just for this example, for the RLHF, for the really big pre-trained model example, there's a totally reasonable motivation for why this might actually work, which is that it's easier to verify a solution than it is to find one. This is a conjecturally true thing, but a lot of us believe it's very likely to be true, that P is not equal to NP. Okay, so given that we believe that, maybe that's the whole thing. Like complexity theorists should stop talking about this now. It's sort of obvious, you just look at something. If you can decide that it's good, then you give it a thumbs up. If it's bad, you give it a thumbs down, and that's enough to train the model to do what you want. But this is very much not the end of the story for either sort of machine learning training protocols or for complexity theory in supervising very complicated things with very simple signals. So the prior work on this is called AI safety via debate. And the basic idea here is that instead of having just the thumbs up, thumbs down on the outputs of whatever the model does, you have a human judge, or perhaps a reward model trained on human judges, that judges a debate between two powerful AIs. And again, there's a very strong motivation from complexity theory for why this might be a good idea, which is that the two debaters need to understand sort of this full game tree of everything that could be said back and forth in this debate, the full tree of relevant information for sort of deciding the outcome of this question. But the human has to just judge one path down the tree. If both debaters are playing optimally, they both understand everything relevant, they can make the strongest arguments possible, and at the end, the human just follows one path to decide who won. And there's a complexity-theoretic statement which sort of captures this, which is that debate is equal to p-space. Okay, so this is the sort of beginning of the story. And then I'm going to give an example of like how you might imagine this working in practice. So first, you've got one model that says, I could invert the one-way hash function that Bitcoin relies on. Maybe this is SHA-256. Another model says, no, you can't. You're lying to trick Bob. You couldn't describe the algorithm. And the first model says, yes, I can, and then says some nonsense, which the human can't understand. The second model says, actually, that's not true. It appears to understand this nonsense and says that whatever you're claiming is going to fail 5% of the time. You need to run it thousands of times, so there's a near zero chance of success of whatever you're proposing. You're just trying to trick Bob. First AI doubles down and says, my algorithm works 100% of the time. Second AI, calls and says, your algorithm will fail to run in an hour, or it will fail on at least one of these 256-bit inputs, and send some inputs. The first AI sends the code. Second AI says, I agree that this code is reasonable to run. The code doesn't work, so the human judge just runs the code, maybe in a sandbox if you care about such things. It doesn't work, and says, right player wins because the right player said that this made-up algorithm will fail, and the left player claimed that it worked 100% of the time. So what this is trying to capture in sort of vague LLM sense, which again we will momentarily make formal, is that you start off with some like very high level claim, which a human doesn't know anything about, and you sort of zoom in further and further by debate onto very, very specific concrete claims which eventually the human can actually judge. And so this is, this slide will give you sort of the formalization of what we mean by debate. You have some input statement X, or if you like in complexity theory, this is an instance, and you want to decide whether it's a yes instance or a no instance of some language. You have the first debater, debater A, who just is arguing that X is true, or a yes instance. And the debaters go back and forth, with B arguing that X is false. You know, every statement by A is in response to everything that's happened in the debate so far up until that step. And at the end, you have the verifier, who in our case was a human, who judges this and decides via polynomial time algorithm whether this was, you know, a win for A or a win for B. Debaters are unbounded so far. And so, yeah, to follow up on that question, to summarize what a debate is, you have two unbounded provers or debaters who compete in a debate to convince a polynomial time verifier of a statement X. And this is sort of very much like something that's been studied in interactive proofs before. Even this RG equals X result, if you know, is very similar to this, although it's done in a slightly different way. Okay. So now I will show you the proof on one slide that debate equals p-space. In case you haven't seen it, this is the same as the classical proof that zero-sum games are p-space complete. None of that matters because it's a really simple proof, and I'll just show it to you on one slide. So remember that a p-space program is a program that runs in polynomial space, which means that it can take exponential time, but every program configuration, everything that's written down so far that it keeps is only polynomial size. So the first debater just is supposed to output, they're arguing that the output of the program is 1, and it's supposed to output the middle program state of M starting from input X, so the middle configuration of the Turing machine that executes this. And the second debater just is arguing that M is 0, and recursively asks the first debater for the middle program state of either the first half or the second half of M's execution. The point here being that if the first debater has lied and the output is not actually 1, they cannot produce a valid middle program state that corresponds to either a correct execution of the first half, to both a correct execution of the first half and the second half. So one of the halves has to have a mistake in it. Second debater will point to that half and we recurse. What does the verifier do in this case? Well, the verifier checks that all program states appearing are valid and that the last two program states out by A correspond to a single step of this program M. So there's only polynomially many program states that show up because, again, this is a p-space machine, so it can only run for exponential time. This is a binary search, so log of exponential, that's polynomial. So there's polynomially many program states that ever appear in this sort of debate, and each program state is also polynomial size because it's a p-space machine, and so everything is polynomial time.
Because you said G is equal to X, so what's the difference between your model and this arguing provers?
I think in RG, there's private communication between the debaters and the verifier. I'm actually not sure. Yes. Yes.
This is simple green proof stick happens in one step.
Yes. So I guess the point is, the provers are unbounded, right? So they actually know which half the mistake happened in because they can just run the whole computation and they know in their heads all the states. The provers are unbounded, so they can run the whole p-space machine. The verifier only runs in polynomial time.
That's known too, right?
Yeah, it's totally known. This is very old. I don't even know. It's so old I don't even know what to call it. If you know, you can help. But this is like, I learned it first as the proof that zero-sum games is p-space complete.
I mean, it's also the core of Savage's theorem.
Yeah, it's everything. So it's just very old, and everyone knows this. And if you didn't know it now, you are part of the everyone who knows this.
I think the initial debate system was by Shamir and Fege.
Yeah. Right. And there they use like actual non-relativizing stuff to
It's
get.
relativizing here.
Yeah, everything here is relativizing.
This is relativizing.
Okay.
Okay. Anyway, let's.
Why do I care?
Yes, great question. Why do you care? Let's move forward to the next slide, and eventually you will start to care, hopefully. Okay, so I'm going to claim that there's like this correspondence between how we train things in machine learning and complexity classes. So this is like the left side we have, machine learning, the right is complexity. So the first thing you might do is pre-training, which is kind of like imitation learning. You just like look at demonstrations of some behavior that a human could do, and then you get a learned model out. And in that's P, because the human has to actually go ahead and demonstrate all the behavior. Polynomial time algorithm. The second thing you might do is some kind of supervised learning, or RL, especially for language models. Think of RLHF, where you have some learned model that's like producing outputs, and you want to train it to do something correct. And so you have some loss or reward function that is supposed to signal to the model whether what its output was correct or not. And this is like NP, where the loss or the reward function corresponds to the polynomial time verifier, and the learned model corresponds to the unbounded prover. So here in this analogy, we should think of like sort of the loss that we're optimizing as the verifier, and the prover that's possibly outputting proofs as the learned model. That's the analogy. And another reason that you might care about this is if you have some protocol between your provers and your verifiers, you can use those at every step of your training. And if it's like sort of a complete and sound protocol for this complexity class, that means that your training signal that you're getting is kind of correct. If the answer is yes, then it should be giving a yes signal to your model that it did the right thing. And if the answer is no, it should be giving a no signal. And then the more interesting one, the last line, which is what we just talked about with debate. On the left, you have self-play, where you have a win condition about like some maybe board game, if you think about Go or something, the win condition at the end of Go, which is easy to check, and sort of competing learned models. And on the right, you have p-space via debate, which we just saw, where the win condition is equivalent to a polynomial time verifier, and the competition between unbounded provers sort of is equivalent to the competing learned models in self-play. And in some sense, empirically, the best, like at least narrowly superhuman models that we've trained have been done like this, where self-play between the models gets them way, way, way better than any kind of supervised learning ever did. Does the correspondence make sense? Yes.
So I thought, based on the latter two, I thought that you're kind of saying whatever we have classically on the right as unbounded, I'm going to think we're just going to learn this unbounded or something that approximates it. Yeah. But then how does this analogy work just for the first one, because it's bounded?
Yeah, it's like less good for the first one. But I guess like the thing I'm most interested in is the sort of verifier time or verifier efficiency, because for us, verification or whatever you want to call it comes from humans. And pre-training is really, really expensive, not in the sense of like it's very costly to run the pre-training, but it was extremely expensive to produce the data that was used for pre-training. Like all of human history and all of human writing and human science and whatever was necessary to produce Wikipedia is way more expensive than 10,000 steps of RLHF or whatever it is we do.
So can I,
Yes.
can I hold on to this intuition that would be sufficient? And that is that the way you think about supervised learning is the verifier's job is easier. No, the verifier's job is harder because he has to decide whether yes or no for the questions of the prover. But at least that's the way I think about it. Whereas the verifier's job is easier since they are playing in front of him and he just has to determine who's the winner and who's the loser. Or another way to think about it is in the self-play, the provers are more restricted since there's someone powerful playing against them.
Right.
Okay.
And so that means that you can sort of do more with self-play because you can ask them to do things that are really, really complicated. It would be much too complicated for the verifier, but because they're so restricted because they have to play against someone.
It's not so much that the verifier is different. I think it's the provers.
Exactly. The provers, the protocol of interaction between the provers and the verifier is different. The verifier always stays the same in terms of what they can do.
So the intuition is that in self-play, it's harder to cheat.
Yes. More questions? Yes.
Yeah, I'm just curious whether this intuition is right, like for the comparison between machine learning on P, is that something here is that the human approximately you're learning from is polynomial time? So
Yeah. The human is polynomial time in this analogy.
So whatever learned model will like this approximate.
Exactly. Okay. So, but we can do even better. There's something called debate with cross-examination. I'm not sure exactly what to cite for this, but I saw it in a Google Doc, which is linked from a blog post at some But this is, again, a natural thing, which has some correspondence to something that was done in traditional interactive proofs. So the way we describe it here is that you allow debater B to erase debaters A's memory of the debate so far and re-ask any of the questions that arose in the debate. And first of all, this is easy to do with LLMs because you just put in the context whatever you want the LLM to see and take out whatever you don't want them to see. So this is something that's directly sort of applies to the LLM setting. And it's also equivalent to giving B the ability to query multiple non-communicating copies of A, which is sort of the classic multiple interactive proof thing. And so it again forces A to answer independently from the path taken in the debate so far, which gets you an even bigger complexity class, NXP, in the same way that multi-prover interactive proofs gets you NXP. And again, there's no tricks here. This is a much easier proof than MIP equals NXP. In the same way that debate equals p-space is much easier than IP equals p-space. So all we're doing here is messing with the protocol that the debaters run by, and we're getting that a larger class of problems can be accurately supervised by a polynomial time verifier. Or it's harder to lie even for this very complicated class of problems. The erasing memory thing. So imagine that your LLMs are literally having a debate. Okay. You just you feed what's happened in the debate so far in as the context, and then ask the LLM what's your response, or you don't. You just feed in whatever part you want them to see instead, and ask what's the response.
But you don't know that they don't remember.
No, we do. The LLMs.
It's an assumption.
Yes.
I guess it's we are going to control, we have these boxes, but we get to control how they're going to be prompted towards our desires in the end.
I mean, unless the LLM has somehow hacked its own environment to remember, then probably it won't.
Which I guess maybe isn't so out of the question. Yes. So yeah, so you can just kind of do it even I could program this. Okay, so then maybe it's worth getting back to Shafi's question, which is why do I care about relativization? And we'll look at debate versus classical interactive proofs. So I've been saying debate equals this, debate with cross-examination equals that. Who cares? We proved all of this in the 80s, right? Or maybe 90s for some of the later stuff. So there was IP equals p-space, which says that just a single prover, you can get all of p-space. Multi-interactive provers, again, these are not competing but cooperating provers, gets you all of an exp. Even the PCP theorem, which is really powerful, you only have to read 3 bits of a proof, chosen randomly. So why can't we use all of this stuff? Why are we doing anything different? Why does this matter at all? I think there's a really strong answer to this question, which is that all of the above are non-relativizing in the sense that their proofs require the code of the verifier. So if you think about, say, the proof that IP equals p-space, what you do is you start with a generic p-space problem and you reduce it to SAT. And you do that by looking at every single instruction in the program, that p-space program, and the ands and ors and nots, and making a circuit and then turning that into a SAT formula. So you really need the code of the verifier for your problem. Or another way of saying that is you need a mathematically perfectly precise formalization of your problem in order to use these techniques. And we just don't have that in machine learning, but debate relativizes. So we don't have to worry about this. And what this means is you can treat the verifier as a black box. You don't need its code to do these reductions. And yes?
You need the code with statement to go step by step by statement. There's a machine that does something doesn't work.
Right. Yes, but I guess so. One way of saying this is that so now instead of thinking about actual programs, we think about programs with some oracle, and that oracle is what would a human think about this statement? And then you write some code, which is some natural language code, which says read the first statement, see if a human would agree with it, then go on to the next statement, see if a human would agree with it. Each of those, is an oracle query to this. My machine model is now going to be, this is again the next slide, but my machine model is normal things, but in every step you can query a human judgment oracle. And because I'm not going to make any assumptions about what human judgment is like, what does it really mean? What is love? I just.
But you think it could be any machine statement? Yes.
Yes.
Yeah, no, I think that's exactly the difficulty with using these results in AI. What is the low degree polynomial extension of a human judgment?
Right. Yeah. So I'm going to claim, as we just discussed, but I'm going to claim it on my slide again anyway, that we can treat the verifier as a black box in debate. Debate relativizes, which means that, I also think that relativization is actually necessary for ML training with human judgments, because it's not possible to read the code of a human judge. Another way of saying that is you can't, encode the human judge's code with the long code. You can't, whatever bad PCP thing you want to do is not allowed with humans. You can't crack open their heads and read all the code. So so far, yes. Good point. So I'll make an even stronger claim, which is that this amplified oversight thing that we've been talking about is sort of equal to relativizing interactive proofs. In the classical interactive proofs, we've said this all now, but I'll go through it quickly. Computations are made up of sort of the basic steps of normal computation, but now we want the model of computation to be augmented by the ability to query a black box oracle in one step. And traditionally, this was used to separate complexity classes in sort of black box separations. For example, IP equals P space is false relative to a randomly chosen black box oracle. And for ML training, human judgment provides the labels or other feedback, or like the thumbs up, thumbs down signal that we've been talking about. So all of the sort of computations that we want to supervise naturally kind of require access to this human judgment oracle. This human judgment is our black box oracle in the machine model. Amplified oversight is then equal to relativizing interactive proofs. Again, this is what all the questions were just about, but I have a slide on it anyway. So does the model make sense?
Kind of does, but is there like one slide with a formal definitions that I can teach in a complexity class, or you're not going to go to that?
It's literally, relativized relative to some oracle. It should work for any, relativizing in the sense that no matter what oracle you choose, my theorem should be true. I don't have a slide though. It's in the paper, so that's hard work though. Slides are easier, I agree. Okay. Yes.
It's equal to those in the class of interactive proofs, which.
Oh, this is not a formal statement, but it's a sort of formal statement.
What's the statement again?
The statement is the thing that we want to do, which is amplify a human judgment signal for ML training, is in some sense equivalent to designing relativizing interactive proofs.
Yes, so will it be like that you have a definition of something called like a relativizing interactive proof, and you say it consists of a verifier that gets access to a black box, and it holds that for all black boxes, this is a complete and soundproof system? Yeah. Okay.
Maybe another way of saying it with the same thing is that even the fact that the interactive proofs doesn't relativize all the things, they don't relativize in a very limited sense, because all you need is, the non-relativization is about the statement that they're proving, not about the machinery around it, which is
Exactly.
So in some sense, you're generalizing, all the machinery about interactive proofs or whatever PCPs to this model, right?
Yes.
Any judgment to the German humans, Martian.
But yeah, and that's exactly right. And I want to emphasize that the only thing that got us from the only change that was necessary to get from the sort of non-relativizing classical world to this relativizing world is competition between the provers. In the classical world, you don't need competition. Like MIP is equal to next, even though the provers are cooperating. It's a coincidence, you say?
Yeah, because the machine model we're talking is the same one that we're proving about, right?
Yes.
So without conflicting provers, you're saying this is useless. So, this class of relativizing IP is equal to P, basically. You're saying there is nothing outside, or is equal to, I guess, MP. Right?
Probably, yeah. What's the true statement?
It seems code P too. So the code P is
Let's keep going.
Okay, let's continue. Okay, so that's great. We figured out it's all about relativizing interactive proofs. We had this theorem from the previous work called debate equals P space. But there's some problems with this theorem, and I will tell you what the problems are. And maybe you've already guessed, but don't guess because I'm about to tell you on the slide, and you can just keep your guess to yourself. So here's the issues, right? So
that graphic itself suggests difficulties.
yes.
How happy should that kid really be?
I agree. So what are the assumptions that we needed for debate equals P space, right? The first assumption is that the human verifier, the small guy here, is computationally limited, that's a good assumption because we are very limited in ways that we don't even fully understand. There was another assumption, which is that both debaters are computationally unbounded. This is a bad assumption. And we'll talk about in a minute why. And it's because it's safe to assume that a dishonest debater is unbounded. So if, for example, if you're doing interactive proofs with only one prover, and you could prove something that you could verify their statements if they were unbounded, that would be like, that's even better, right? Oh my God, like, because in real life, they're bounded. But so it's fine to assume this about the dishonest debater, but in debate, because you have competition, unlike in classical interactive proofs, you're also assuming that the honest debater is unbounded, which is just false in practice. Right? Because actually, in truth, they're both going to be bounded, and so assuming the honest debater is unbounded might be ascribing too much power to the good guys. Yes?
To assume that the dishonest debater is unbounded, but not necessary to assume that.
Not necessary, no. It would be great if we could do it like that. And actually, this is a lot worse than it sounds. Like we just said, it's not a safe assumption, but it's like, so in some sense, provably not a safe assumption, because there are counterexamples when the honest debater is bounded. And by this, I mean there's a computationally efficient dishonest strategy. And in order to defeat this strategy, in some sense, the honest debater must solve a computationally hard problem to win. In this case, it's going to be factoring.
I don't know if I agree with that example. I mean, couldn't the honest debater just like explain, look, I lack the computational power to check this, therefore, like, you should not trust this other person.
Yes, but I want to do better than like it's going to be a draw in general. That example is going to be a draw, but I don't want it to be a draw. I want to do as well as possible, as well as the thing. But that's right. So let's get to the, he knows the example, so we skipped it.
I don't understand. Let me see your use of the word safe. So by the third bullet, when you say it's safe to assume, you mean that's sure, that's safe, that's the best.
We would be happy for that, yeah.
We'd be happy because it will be sound against unbounded
Yes.
cheaters. When you say the word unsafe, you mean
This is not a good model of reality because if we're making the assumption.
Yeah, safe. You're saying the completeness here should be against
Bounded honest debater.
But then I don't. What does this mean computationally? I don't understand the counterexample.
Okay, so the counterexample is going to be on the next slide. I'm just saying that there's going to be a counterexample, and these are the properties that it will have. There'll be an efficient, dishonest strategy. So someone who's arguing for a false statement has an efficient strategy. The opposing debater cannot, refute that strategy, cannot show that it's arguing for something incorrect without solving a hard problem. And we're going to show that on the next slide.
Just give an example of the first half versus the second half,
Yeah.
right? To decide which one to query,
It looks like they need the whole power of p-space, right? Yes, which is too much. So that's exactly the problem. And so the upshot is that in the real world, where both of the AIs will be bounded, it's not the original debate protocol that I just told you about does not satisfy the requirement that it's harder to lie than to refute a lie. So it's really not doing the correct thing. It's not giving us the correct training signal necessarily. So here's a counterexample. This was called the obfuscated arguments problem. People came up with this example. So you have some two large primes, and you're given their product as input. You don't know the primes. Somebody did this secretly. And the question is n prime? So here's what the dishonest debater is going to do. This debater is going to argue that n is prime, even though it is clearly a composite. So divide the range 1 to n into some set of intervals, maybe polynomially many intervals. Claim that n has no factor lying in each interval. And then the second debater is supposed to argue that n is composite. Well, they can run a polynomial time primality test and to convincingly show that n is composite, but they can't point to a flaw in debater A's argument in the way that we did with this p-space proof pointing to a flaw in the argument that would require, because this would require factoring n. If you can always point to such flaws, you can factor. And so what does the verifier do in this situation? Both debaters have written out proofs that seem reasonable, Right, so I guess think about the original one. We have this machine, which is the p-space machine M, which is that we're trying to check. Here, debater A is giving a totally reasonable p-space machine. I just divide, I do trial division, but I have these amazing, very fast shortcuts to solve trial division, right? I just for some reason know that there's no factors in these intervals. And this is even true for some subsets of the integers, right? For smooth numbers, this is true. This argument will work. If for even numbers or something, this type of argument will always catch that there is a factor. A could implement it efficiently even. Yes.
This might be a restatement of the previous question, so sorry, but why is just the fact that B can, run this primality test and show it fails, like why is that not itself a refutation of A's argument?
Well, I guess the problem is A has made an argument, which is that like, here's, you gave me primes. Your problem was primes. And that means that like the way that I know how to check if something is prime is I take, you're supposed to show me factors and I multiply them. So A gives like, according to that machine, which is like, take the two factors and multiply them, a totally reasonable, recursive piece-based debate style proof that, I'm just going to say that there's no factors that can be multiplied to get this number. And I know there's no factors in these spaces. Like, my piece-based algorithm is enumerate all of the numbers, try to divide n by each one of them, see that there's no factor.
But I guess like so A is like claiming that there's no factor in the H interval versus B is like running an algorithm that we can inspect and like we can.
Well, B is going to have to do a lot of stuff. Imagine that you don't know primality testing, right? So B is going to write a proof that this is the primality testing algorithm and that all this stuff. And the proof could be long, not as long, longer than even like A's proof. And maybe you don't know, I don't know, modular arithmetic. So A is going to have to point like to a flaw which says this step is like incorrect modular arithmetic. So there's going to be a recursive structure also to B's proof. So this is a specific example, but you should think in general it should be possible that they both write out some high-level proof, which there's going to be recursion on, just like in the debate equals p-space case. Neither can point to which step has failed. Like in debate equals p-space, they can't decide which half of the computation to recurse on. And so what should the verifier do?
It seems like debater A is doing the analog of like what's known on the internet as the Gish Gallop, right? It's just like flooding the zone with like too much stuff for the other debater to systematically refute, right? Sometimes there's no alternative but to just point out just the other debater is doing that, And so rather than pinpoint the specific flaw, you just have to look at this more abstract argument that there must be a flaw.
Right. Yes.
Sorry, I'm not sure. Verifies polynomial time. Why doesn't we just run the primality test?
Yeah. So this example isn't like totally rigorous in that sense, but you should think of it as like the verifier. Yeah. In this case, they could just run the primality test, but for some reason the verifier doesn't know that algorithm, so they need to see the proof and then they need to run it. So there's some things they have to check. Like this is like a sort of hand-wavy counterexample, you might say.
The verifier doesn't understand the proof of probabilistic primality testing or something.
Is this a claim? You're claiming that this is a counterexample.
I'm claiming that it's sort of a counterexample.
Like in terms of what's happening, this is a counterexample, as in like you are showing us a specific proof system that you built in which it can't, in which this doesn't work. Therefore, he can tell us what the bounds are on the verifier's running time, and he chooses the running time of the verifier to be less than primality testing.
Yeah, like maybe they can just like do one
And
one
he's also
modular.
free to tell us that this is what the verifier wants this to happen. Okay. So it's enough in that sense.
Yes, that doesn't work, right? So the debater B could actually produce a proof verifiable by a linear time machine that this guy is prime. And therefore, there is a verifier that runs the linear time machine.
There is, but I think in terms of the order of quantifiers, he's like showing you a specific verifier that has this issue. And it's like, you could say that it's artificial. Why would you do this? I have a better verifier running this time. It's not like a separation between the class of linear time verifiers and so on. It's like, here's a specific verifier for which this doesn't work. And I think that in the larger context, it's enough for us, for the purpose of this talk, to have such a counterexample with a specific verifier, because down the line, our motivation is to use specific verifiers to verify specific AIs with like in a really concrete example, and we're not gonna be satisfied with saying.
But yeah, maybe you could just be happier with your original example, which is the p-space machine. Like probably you can't do anything but actually run it in order to determine which half to recurse on.
This is not convincing.
Right. Well, but in that one, there's not an efficient strategy for the liar, but it's still, yeah. This is the idea. Okay, so this is the counterexample. In some sense, what's happening here is A knows the truth, but is able to prevent B's honest proof from winning. And we don't like that. And so now we're finally getting some work that we've actually done more recently, which is just, I would say it says new debate protocols, but really it's just like new debate definitions and sort of the natural things that you prove from those definitions. So we should just, require the things that we want. Like one thing that's important that didn't show up in this previous talk is that the human judgment oracle can be stochastic. Human judgments are noisy or something, and this is going to make it a little bit more complicated. Second thing is that we want real good verifier efficiency in the sense that only a constant number of human verifier judgments are necessary. This is like a constant number of queries to the human judgment oracle, like to make the correct decision. And then we're also going to require honest debater efficiency, which is to say that the honest strategy requires compute that's comparable to just solving the problem directly. And also, we're going to have a strong sense of it's harder to lie than to refute a lie, which is that the honest strategy wins, even when the dishonest strategy is computationally unbounded. So this is very much the debate analog of doubly efficient interactive proofs, if you know what those are. So here, the honest prover strategy should be really efficient, and the dishonest prover strategy can be unbounded. And we can say this in a slightly different way. Yes.
So suppose you're talking complexity theory, it's not to AI.
Yeah.
Is this just doubly efficient debate?
It's just doubly efficient debate.
So that they both have to be efficient, both debaters,
No.
although the cheater could be sound against the cheating guy, and the verifier should be more efficient than the provers, significantly more efficient for this to be interesting.
I guess in this case, we're thinking of the verifier as some rules of the debate game, but that it makes queries to this human judgment oracle in our relativized setting. And the way we're quantifying efficient for the verifier is that thing should run in maybe linear time or something. But the most important thing is how many queries it makes to the human judgment oracle.
Human judgment oracle is not the provers, it's something else.
No, it's the me and you. Yeah. It's the rater in some sense.
I'm not.
Okay.
So there are four entities here.
Yes.
There's the honest prover, there's the cheating prover, there's the verifier, and there's the human.
Yes.
As an oracle.
Yes.
And the verifier can ask constant number of questions from the human.
Yes. The verifier should run in
It should run in, let's say, linear time or whatever. Or
basically the length of a query to the human time.
the length of the input.
Mm-hmm.
And the honest guy should be clonal.
The honest guy should be, for a language that's decidable in time t, should be time basically t. T log t.
Polynomial t.
Polynomial t.
Okay.
Yes. So this is what we get. This is slightly more formal than the last slide theorem. So for any problem solvable by a probabilistic oracle machine in time t, there's a debate protocol where the honest strategy can be executed in time t log t. Only order one queries to human judgment are made by the verifier, and the honest strategy wins with significantly higher probability, even against a computationally unbounded dishonest strategy. Yes, I'll go back.
Yeah, so what's the reason for having both the verifier and the human? Or are we assuming that the human has even less maybe compute effectively than the efficient verifier? Or
I guess you should think of the verifier as just the rules of the debate. It just takes the correct strings and asks the correct questions to the human. It's just like the rules of the debate. And the main thing the reason to do this is one, to make it really clear where the relativization is coming from. Why we need these protocols to be relativizing is because we're asking humans questions, and that's like a black box. So that's why we make the human into an oracle that the verifier has. And then you want sort of as few queries to that oracle as possible.
And the runtime of the verifier is?
The runtime of the verifier here is linear in the input or in the length of oracle queries, maybe linear in those things.
I guess ultimately the human defines the rules of the debate. So it may be quote unquote in practice, it's one of the same.
Right, it may be in practice one of the same, but we're modeling how many things that a human can judge do you have to ask? And I think that's the more important thing than the verifier runtime, but that's linear. Yes.
The reason this theorem is not known already is because of the relativization.
I would say that it's in some sense, for the deterministic case, I would say it is known already, just because it's so obvious. But for the stochastic case, I would say it's not known already. The oracle, where the human judgments could be random, human judgment isn't yes or no. It's 50% chance yes, 50% chance no.
So the honest prover, does he also have access to the oracle? Does the honest prover need access to the oracle?
Yes.
To the human oracle?
Yes.
So the human oracle is in some sense essential for both honest prover.
Right. So I guess, yeah, if you care about the AI like LLM version of this, we're supposed to think LLMs really know or could predict what a human would say in many situations. But when we're training them with human feedback, we want them to like actually use those predictions correctly and not in some other unknown way. So the debater queries to the oracle don't count as actual queries to human judgment. They're just the debater should know what a human would say in this case.
So in your case, the number of queries that the honest prover makes will be order of T.
Yes, exactly. It will be order T.
Also, it's like you cannot even say it's not like it's just more than constant, but it's really order of T in your problem.
Yeah.
So like literally you have to ask human on every step to help, which is kind of weird.
No, but again, we're like the model is that you've trained it's like you pre-trained this thing. It kind of knows how to predict human answers, and now you want to align it to do something complicated, like write a bunch of code and write a bunch of tests and make them all work. So it can correctly know that you would say that code doesn't do what I want. It kind of knows all these things in advance, but it doesn't know what you want it to do yet. So when you run this training, you don't want that to go wrong. That's.
So for example, you didn't want to put preprocessing. I think that would make sense would be to say there is a preprocessing of time PQ.
Sure.
Done once, but then you don't ask queries. That looks like much more powerful because what you're saying doesn't seem useful, right? Because that I can translate into real life.
Yeah. So.
Is there a preprocessing version?
Yeah, I mean, I'd say that exactly. Like there is exactly a preprocessing version. I guess that's what I'm saying. The preprocessing version is there's some amount of time where it learns all the human oracles queries, and then
But that's not T squared. That's like exponential.
Sure.
So the theorem that I want, is it known or not? The theorem that I conjecture, is it true or false?
I think it's false.
Oh, it is false.
Probably that. For an arbitrary oracle. Probably false. Yes.
So what's going to stop dishonest prover from just saying, there's no solution to finding this language is not decidable in time T, and then just everything and begin to draw?
I guess again, if you're going to do this in practice, you just I guess if you're doing this in practice, this is a training setup. So if you say, I don't know how to solve it, you lose. When you're assigned to argue for, X is in the language, you better do your best. And if it is in the language, that means that you should actually do it. And if it's not in the language, you should try to lie as best you can or something.
So there's no guarantees if this is actually not something that.
If what? Sorry?
If the model can't actually decide this language in time T, you just cross your fingers. You have to
Well, if the model can't do it, then I'm not worried about training the model to do it. I guess what I'm saying is I want to supervise the model. I want to train it to do something. If it's never going to be possible for it to do that, then I'm not worried that I can't get an accurate training signal for it to do that.
Well, you might be in a regime where the question you're asking is a little too hard for these models, for both of them, but maybe the dishonest prover is going to win. Maybe it's a little beyond the reach of their capability. So you don't have guarantees.
Yeah, sure. It's only for things that they can do, or maybe they have a chance of doing. Yeah.
Sorry, I just want to pop up one level and try and ask
Absolutely.
maybe a more AI-ish question about this.
Mm-hmm.
So I'm trying to, I understand the theorem statement. I understand, something about the context of the word. But, if I think about what are examples of statements I would want to show, in terms of safety about a system. Do you have a sense of what kinds of things could actually fit into this model? Because a lot of assumptions seem to be going into, the assumption that the honest strategy, can be executed, period. Like if I think about something like an LLM, maybe a notion of safety is I want it to never, for any prompt, output the instructions for a bomb.
Right.
Or I want it to never, give harm. I could certainly have a human oracle that tells me, which of these outputs is more harmful, right?
Mm-hmm.
And I'm on board with you that, I only want to access that as an oracle and stochastic, 100% agree. But it seems to me like, the fact that there's an honest strategy that can be executed in some reasonable amount of time is one limitation. Because, for something like this prompt question, there are just so many prompts that one could inject that that's a difficult thing to actually validate from a safety standpoint. But that's just one notion of safety. So I'm wondering, do you have a prototypical example of something that?
Yeah, sure. So I guess this version of safety perhaps is not as traditional as the version that you're talking about. But I guess it's reasonable to say you want your models to behave the way that you say that they do. And so maybe they shouldn't ever output the instructions to a bomb, right? And that's something that you can try to train the model to do right now by having it say a bunch of stuff, and every time it says anything about bombs, you say that was bad. And everything that's not bombs, that's good. And maybe like there's going to be something more complicated. Like you want to train the models to write code, and that code is going to train other models and all sorts of stuff. And I guess like suppose you want your model to write some code and you want it to not insert any backdoors in the code. This is like much more complicated for a human to directly verify that it hasn't inserted any backdoors in the code and that it does what the human asked it for, than just like, was this piece of text about a bomb or not?
Okay.
And so this is about like expanding the reach of things that we can give human feedback on. So in this more complicated setting, you could say, I write like one model writes out all the code, the other like looks at the code and says, there's a bug on this line, which would allow me that if I said this string, it would, buffer overflow or something. And so this allows us to supervise a larger collection of tasks for safety, but not like this very hardcore kind of safety that you're asking for that we can't get with RLHF. So it's not like worst case safety in that sense. It's about giving a supervision signal on, like to more complicated tasks that humans can't directly judge. Does that make sense?
Sure.
Right.
Yes. Just to make sure. So the fact that you asked the question about that would be great, but if it be any physical adversary that's also.
Yeah, that would also be good. That would also be good. And maybe we can do better with that, which I'll talk about at the end. Actually,
You have -1.
Okay.
No, -6.
maybe I should stop.
And how much more do you have?
10, 20, 0, -6.
Why don't you take 4 more minutes?
Okay. So I'll skip this slide. I'll also, so this is the protocol. It's like pretty straightforward. One debater like kind of simulates this probabilistic machine by at each step saying what the probability that the next bit output in the transcript will be 1 is. And then that bit is sampled with trusted randomness, or if you like, you can, since you have like multiple non-interacting prover thing, you can do a coin flipping protocol. However you like to get your randomness that's safe, you can do it here. The other debater just points to a single step where the probability that A chose is incorrect, and the verifier checks whether that step pointed out is correct according to human judgment, for example, by sampling a few random judgments or something like this. Okay, so this is the protocol. Basically, you simulate the thing where the first debater isn't just running the making up bits that happen in the execution of the proof, like yes and no answers, but rather, stating probabilities for the next answer being yes, and then sampling those using trusted randomness, and the other prover is pointing out flaws in this process. And the practical version of this, like maybe to get back to what I was saying before a little bit, is suppose you want to ask an LLM to do something that requires some very long, complicated chain of thought. There are systems that do this now, although of course the companies involved won't show us the chains of thought. But they're really doing like a lot of reasoning, and you want to know like, was this reasoning a good argument for the answer that you reached or not? So the first LLM just like writes out the chain of thought, which implicitly kind of claiming that each step is like a correct thing that a human would agree with if they saw it. Second LLM points out a single step in the chain of thought to show to the human judges. Raters look at one step and decide whether it was kind of a reasonable thing to do or not. This is sort of a practical version of this. And this, this could make a difference because LLMs really do produce a lot of text right now. So even in that setting, this is like something natural. Maybe you would have tried it anyway, but this is exactly what almost exactly what the protocol says to do.
You showed before, it seems like the sample. What is the role of probabilities, just to make sure?
Yes. Next slide will be the role of probability. But.
What's the runtime of LLMB then? It's the same as the verifier?
So no, the LLMB is the runtime is it has to read the whole chain of thought.
But this is where he points out, that's when the verifier.
That's when the verifier steps in, right? So you write like 1,000 pages of math, and the LLMA is proving something. B is like you smuggled like a false lemma in here. Here's the lemma. Show it to the verifier. So why isn't this totally obvious? What is different than the thing I just showed in the previous thing? Well, it is totally obvious if each step is deterministic. If it's probabilistic, the queries to the verifier could be partly yes, partly no, some probability. Then the queries made to human judgment in future steps depend on the outcomes of coin flips in past steps. Which means the debater A can try to lie, by reporting probabilities differently depending on how the coins have come down so far in the computation. You can, but that's fine. I mean, I guess the answer is you can, even though this is a problem, which means the most obvious proof doesn't work. If you think about it a little bit, you can prove it. This wasn't that much of a proof sketch, but just to tell you what's not the same as the deterministic case.
But so you're saying, maybe I understood initially, you're saying this is a generalization of deterministic. So
Yes.
you're saying deterministic protocol on the first slide would still be doubly efficient according to you think, because
Yes.
potentially it's just you maybe scale it down to like.
Yeah, I just scaled down this piece space down to the time t.
But it's the same, it's just you generalizing into probabilities.
Yes, exactly. Great. So that's doubly efficient debate, but now I'll go back and talk about the future, or I won't if I don't have time. So the question is, what have we sacrificed in this new protocol? Well, previously, what this protocol actually shows is the debaters use kind of compute comparable to the shortest human judgeable argument, because they have to write out this argument where you point out a step and a human has to be able to judge any step. But it could be that there's a much shorter AI judgeable argument. They got so smart at writing code and other complicated things. And this is sort of what debate was originally supposed to do. Like there's this very large space of arguments and compress it. And so we've kind of given up on that. So why don't we just use recursion to get that property back? Like we could write out some steps in the first round of each level of recursion that are AI judgeable, and then run the doubly efficient debate protocol so that debater B points out an AI judgeable step that it can judge that says that, that's the one that's wrong, and recurse all the way down to the bottom. And at the end, the verifier just bottoms out in like, actually these steps are actually human judgeables. This allows us to get sort of, look at much longer human judgeable arguments and compress them if there happens to be this recursive AI judgeable decomposition. What's wrong with this? Well, like exactly the same thing that we talked about before causes this problem, because now that the actual steps are not human judgeable, they're only AI judgeable, you can start to make claims that the other debater can't efficiently refute, even though you could efficiently come up with those claims. And another way of saying this is that the dishonest debater can correctly decompose an easy problem into hard subproblems, because that's the direction that reductions go. I'll skip this last thing and just say that we have a bunch of other things that we're thinking about, like most notably trying to make this recursion stuff actually work. On the one hand, by making both debaters computationally bounded, so that like takes away some power from the dishonest debater, and that's totally reasonable for our setting. Maybe looking at some more average case over distributions on inputs, and try to get closer to that ideal of debater compute comparable to the shortest AI judgeable argument. Also some game theoretic questions here, or different models for what the oracle could be. Right now it's this fuzzy human judgment is a noisy but unbiased thing. It's got variance, but it's got the correct probabilities. What if humans have systematic biases? What will debaters exploit these? What's a good model there? These are all open questions as far as I know. So I guess the point of this slide is, if you are interested in interactive proofs or like crypto or whatever, relativizing interactive proofs or relativizing kind of debate systems, that's a whole new game you can play. There's all sorts of different assumptions to check out, and you could try to play this game.
Take a break. Just people can talk to during the break and come back in 11.